in, like uploading to Blackboard, anything like that?
Is that due for this class?
Homework 1?
What?
So homeworks are always due 5 p.m. on Friday.
Okay.
Next year I'm going to change it to 11:59 p.m. because that's the default that Blackboard gives, and then I can be a little lazy and have one less button to press. But this year, 5 p.m. on Friday. So then, as a warning, homeworks 2 and 3 are both due this Friday at 5 p.m. That was on the schedule. These homeworks are not really so, they shouldn't be so time consuming. So that's why I don't feel so guilty about it. A little guilty, but not overly guilty. Let's see. So TA office hours. I didn't hear back about getting a room for TA office hours, but we still want to have them this week. So TA office hours, I tried to edit the class website to put this on, so the information should be on there, but it's going to be, so Wednesdays 4 to 5 p.m. and 7 to 8 p.m. And for this week only, it will be in the Brody Atrium, which is one floor below the cafe. So we're not supposed to have classes in the Brody Atrium. This will be a one-time only location for the office hours, and by next week we should have a room for the TA office hours. So I'm sorry, I requested a room and then I just didn't check back and we didn't get a room, or at least we didn't schedule a room. So it shouldn't really be a problem. I just have to check again on getting a room. All right, so now any questions? General questions. All right. So someone asked me a question about the convolution integral. So the Laplace transform of a convolution. So this is the convolution of f with g, and that's the Laplace transform of the convolution. G of t prime, s t prime. So let's see, is that right? S of t minus t prime. I'm sorry, that doesn't, that's right, there we go. Yeah, that doesn't go there yet. Okay, so so that's the convolution of f with g, and then that's the Laplace transform of the convolution of f with g. And so the way we do it is that we know that we're going to want to have a Laplace transform of f by itself, and the argument of f is t minus t prime. And here we have the minus st. So if we put in an e to the plus st prime and an e to the minus st prime, we're multiplying by 1. So we can do that. And then we rearrange. So we have the integral from 0 to infinity dt, the integral from 0 to t dt prime, e to the minus s t minus t prime, f of t minus t prime, e to the minus s t prime, g of t prime. And then so now we look at the area that we're integrating over. If this is the t-axis and this is the t prime axis, so t goes from 0 to infinity. So we're integrating from t from 0 to infinity. And t prime goes from 0 to t. So here is t prime equals t. So we're integrating that area. And t minus t prime all right. So then we could also think about integrating along this axis first. So if we integrate along this axis first, then t prime equals 0 to infinity. And t equals t prime to infinity. So that's sort of integrating like this. And this we could write as t minus t prime equals 0 to infinity. And if we work out the Jacobian for the transformation, the Jacobian is 1, so there's no factor from the change of variables. So essentially we're changing variables from t and t prime to t minus t prime and t prime. So this is the integral from 0 to infinity d of t minus t prime, 0 to infinity dt prime e to the minus s of t minus t prime, f of t minus t prime, and then e to the minus st prime g of t prime. And now if we just think of this as another variable like u, then this would be du e to the minus su f of u. So this part is f twiddle of s, and then this part is g twiddle of s. So that's how that works. You're not going to be asked to prove the convolution theorem, but you'll have probably quiz or exam questions where you use the convolution theorem where, like, you get two functions and basically all you have to recognize that the Laplace transform of the convolution is the product of the Laplace transforms of the functions. Yes?
So in that second integral, the variable of integration is t prime. So how are we able to pull out functions of t prime?
Oh, of t minus t prime?
Yeah, so you're pulling out functions with t prime in them.
So here's the way to think about it, is that like this integral is an integral over like this big infinite triangular region, all right? And we can organize how we do the integral by saying, all right, like we go along this axis, and then for given position here, we're integrating from here up along the t prime axis, all right? So that's the way we started. That is the Laplace transform of the convolution. Instead of thinking about doing the integral like that to add up all this, the integrand over this area, instead we could go up this axis first, and then for each value here, go from here to infinity, all right? So then t goes from t prime to infinity, all right? And then we have e to the minus s times t minus t prime f of t minus t prime, the integral d t minus t prime from 0 to infinity. And then if we just did a change of variables that t minus t prime is equal to u, then that goes from 0 to infinity. So it's like we're doing it like we change the axes. So here we have t prime goes from 0 to infinity, and then here u is equal to t minus t prime goes from 0 to infinity. So we've gone from what looks like a triangular region to what looks like a square region. And then when we do the integral, it just separates. So it is sort of a little confusing, but it works. I guess what's confusing is looking at it like this, it seems like the Jacobian of the transformation should be a half, because here it's a triangular region and here it's a square region, but the Jacobian is 1. So the Jacobian is that dt prime is equal to the determinant of, so we're changing variables to du and dt prime, where u is equal to t minus t prime. So we get dt du dt dt prime dt prime du dt prime dt prime dt du. So t is equal to u plus t prime. dt du is equal to 1. dt dt prime is equal to 0. dt prime is equal to 1. And then it doesn't matter what dt prime du is, because the determinant won't be affected by it because that term is 0. But I think this is like, so dt prime du, so dt prime du, actually dt prime du is 0. So its determinant is just 1. So the Jacobian of the transformation is 1. So that's how that problem works. All right. So I'll leave that up. All right, so now we're going to take what we've learned and apply it to predict the response of a cell to an external signal using a one-parameter model. And then we're going to look at the experimental results published, I guess at this point, maybe 5 to 10 years ago in a couple of different journals. So there is a raft of papers that came out doing quantitative analysis of signaling in yeast cells, and then later on in human cells. So we worked on the theory. Now we're going to see what the theory predicts for how a cell responds to an input, and then we're going to compare the theoretical results to experiments that were published. So here is, so if you remember, so we have this model where we have yeast cells and there's a nucleus and they're being perturbed by some signal that we control, and the response to the signal is that a transcription factor translocates to the nucleus, and we can see it happen because the transcription factor is tagged with a dye, and we see all the color in the cell concentrate on the nucleus. So the output is essentially a quantitative measure of the signal intensity in the nucleus. So we'll call that x of t. And our model is that the cell behaves linearly. So 0 to t dt prime, h of t minus t prime, beta of t prime, where h is the response function. The dynamics are that the time dynamics are equal to a sort of a linear increase from the input and then a return to the resting state. So s x twiddle x of s minus x at time 0 is equal to the Laplace transform of the input minus alpha x of s. So x twiddle of s is equal to 1 over s plus alpha beta twiddle of s plus 1 over s plus alpha x at time 0. So we recognize that this must be the Laplace transform of the response function, and in the time domain h of t is equal to e to the minus alpha t. So now what are the different inputs that we usually think about? So one input that is very common to think about is a delta function. So we hit the system at time 0 with an impulse. So let's see, doing this. Yeah, all right. So so in that case, beta tilde of s is just equal to beta 0. And all right, so in that case, x tilde of s is equal to beta 0 h tilde, where h is the response function. So x of t is equal to beta 0 h of t. So in our system, that would be beta 0 e to the minus alpha of t. So this is sort of more writing the general result for a linear system. And then for our particular system, the response function is a simple exponential. So to measure the response function directly, you can hit the system with an impulse and measure the response, and the response to the impulse is the response function, as long as we don't have the decay of the initial condition. So if we set up the system so it's at sort of its resting state at time 0, so at time 0, x0 equals 0, and then apply an impulse, the response we measure is just the response function.
What you're saying is that other term only matters if it's not in equilibrium when it starts.
Yeah, yeah. So this term also comes from starting this integral at 0. If we started the time integral at negative infinity, everything would still work, but we'd have to include the input that sets up the system to be at 0 at time 0. All right, the next input we will think about is the exponential input. Okay, so exponential input so here beta of t is equal to beta 0 k e to the minus kt. So I'm choosing this form because if we integrate this part, so if we integrate the input from 0 to infinity, it normalizes to 1. And then beta 0 is an overall strength. So the same way that the delta function, if we integrate over the delta function, it normalizes to 1. So often when we have a delta function, instead of working with the delta function directly, it can be helpful to work with a function that we're sort of more comfortable with. So here, in the limit that k goes to infinity, this becomes a delta function. So let's see. Did I actually do that in the notes? Maybe not. So maybe I'm not going to worry about that. Yeah, I guess I only put that in to say here's a function you can use in place of the delta function. Yep. So we'll leave that one go. So exponential input, we won't work through the details. So next is the step function. So beta of t we'll write as beta 0, and then theta of t greater than 0. So this is how I'll write step functions in the class. That capital theta is the truth function. So it's 1 if true and 0 if false. So instead of writing little u of t as the step function. So the reason is that we'll have other logical inputs in the course, and it's just an easy way of generally writing something that takes an argument and then converts it to a 1 or a 0 based on logical conditions. So there's one problem with this function, and that problem is that if we go out to infinity, everything stays on. And when things stay on, when you go out to infinity, it can cause problems and make it not clear what the right answer to something is supposed to be. So often what we'll do to make sure that we're doing things properly is we'll add on some sort of long time decay. So where epsilon is greater than 0, and then look in the limit that epsilon goes to 0. So this isn't really part of the step function, but we'll just put it there to guide our answer. So for times less than 0, this is strictly 0. For times greater than 0, it starts out as a step function, but then there's a really tiny, tiny, tiny bit of exponential decay to help us guide our thinking about boundary conditions. So then beta tilde of s is going to be beta 0 1 over s plus epsilon. And this, so this is still healthy when s equals 0. So the step function itself is the limit that epsilon goes to 0, and then that gives a 1 plus s, 1 over s, which is not well behaved at s equals 0. All right. Yeah?
So given the boundary conditions, you can come up with any equation you want, and it's good as long as it fits them.
Say again?
That was kind of what your justification was for adding the exponential. You just wanted to satisfy boundary conditions, so it wasn't really
So here's what I'm saying. Suppose that, so we're not going to do it, we're going to take one step to making it formal. But we're not going to make it fully formal because we don't have time for a proof. All right, so say that we're interested in the behavior of a system. So we want behavior to some time capital T. So we're going to be interested in how a system behaves over the next couple weeks. And we're not going to worry so much about how it behaves after that long time. So say that we think about our system like that. Then if we do something to the input after time capital T, it won't affect anything we calculate up to time capital T. So that is, that's essentially what we're saying, is we're going to worry about the behavior of the system up to some long time, and then beyond that, we won't worry as much. Okay? So then what we're doing is we're saying it's a problem when system properties diverge, when they go to infinity. So what we're going to do is we're going to turn off our signal sometime after time t. All right? So really any function that turns off the signal for some time after capital T, it doesn't matter what that truncation function is, we'll still get the same answer up to time capital T.
You just have to be careful, I guess, in picking it so it doesn't affect the current period.
That's right. So what we're doing is we're picking a function. So our function is e to the minus epsilon t, and so here it does affect it everywhere, but in the limit that epsilon goes to 0, this should still hold. So actually, in the limit that epsilon t goes to 0, then the system will behave as if there's no shutoff for time smaller than capital T.
So in this case, since epsilon's going to 0, we could also just take the first term of the Taylor series for it, make it like a 1 over 1 plus epsilon now. And then instead of using exponentially, just have...
Well, that would be, so it would be 1 over 1 plus epsilon t.
Yeah.
Yeah, we could probably have a 1 over 1 plus epsilon t and take the limit that epsilon goes to 0. That might work. I don't know that the Laplace transform would be so easy. Yeah. So the reason why this form is nice is because it's sort of the conjugate form to the e to the minus st. So it's nice to pick a form that doesn't make our problem any harder. So it doesn't make our problem any harder to choose a cutoff like this, whereas any other functional form it would make our problem harder. So that's why we take this form as opposed to some other form. So often there are problems where you have something that doesn't behave quite properly and you want to fix it. And it's nice to fix something in a way that doesn't make things any harder. So already doing the integral e to the minus s times t, it doesn't really hurt us to add on this epsilon t. All right, so so now we have, so x tilde of s is now going to be 1 over s plus, so we have a beta 0 over s plus epsilon. And an h tilde of s. So here, for us, this is 1 over s plus alpha. And now we have to do the inverse transform. So x of t is the integral of ds over 2 pi I from minus I infinity to I infinity e to the st divided by s plus alpha times s plus epsilon. So we have two poles, one at negative alpha and one at negative epsilon. So here's our integral. It goes up the pure imaginary axis. Here's negative epsilon. Here's negative alpha. We can close it like that on the left-hand side, and so we get a contribution from each pole. So each pole gives us a 2 pi I that cancels that 2 pi I. So doing the epsilon first, we get an e to the minus epsilon t over minus epsilon plus alpha. And then the other pole at negative alpha gives us an e to the minus alpha t divided by minus alpha plus epsilon. And then in the limit that epsilon goes to 0, we get a 1 over alpha minus e to the minus alpha t over alpha. So that's 1 over alpha times 1 minus e to the minus alpha t. And I'm sorry, there's this beta 0 over here that I should have been carrying around. So there's a beta 0 in the front there, a beta 0 multiplying both terms, a beta 0 multiplying both terms, and that should be a beta 0 over alpha. So in the end, we can take the limit, epsilon goes to 0, and we don't run into any trouble. What it did for us, though, to put in this cutoff of the input is it moved the pole off of the imaginary axis. So if we hadn't had that cutoff, our pole would have been sitting right on the imaginary axis, and we wouldn't have been sure what to do. So what that boundary condition does is it tells us that really we should think about the contour including the pole at 0. And in the future, when we have a pole at 0, we'll just be including it instead of going through the exercise of adding a cutoff. So the cutoff is sort of like the physical reality of the system is telling us what to do with poles at 0.
I thought our system was consisting of a transcription factor that migrates to the nucleus, right, and accumulates there. Is that our system?
That is our system.
Because in this case, you have the answer telling us that it's dissipating and that the response is not.
Well, but no, so remember that we have two things going on. The system is getting activated, and then it's also deactivating. So our input activates the system, but then part of our system returns the signaling molecule to the inactive state. So there's an equilibrium, and this says at long time as t goes to infinity, the equilibrium is that the state of the system will be beta 0 over alpha.
Okay. So the initial migration is an impulse, then it all happens at once because at time t equals 0, that's beta over alpha, and it's all in.
No, if we plot this function, so here's the, so here, I'll erase this. No, so here's what it says. Okay, so here is time, and our input is a step function. So this is our input. And what it says is our output is going to look like something like this. So here's our output. Okay. All right. Yes?
So is the integral from negative I infinity to infinity of ds 2 pi I of your f of s times e to the st, does that give you your x of t? Is that like a rule then for inverse Laplace?
Can you say that again?
So that integral where you do x of t equals, the integral of the imaginary axis, is that the rule to do inverse Laplace? Or?
Oh, yeah. Oh, yes. So here, like if you remember Fourier transforms, so this was in the notes, but maybe I missed it. So we started out doing everything with Fourier transforms, where f hat of omega is equal to the integral from minus infinity to infinity dt e to the minus I omega t f of t. And then, so S is equal to I omega. F tilde of S is equal to the integral dt to infinity e to the minus st f of t. So that is the Fourier transform. And then the inverse transform, f of t is equal to the integral from minus infinity to infinity d omega over 2 pi e to the I omega t f hat of omega. And the homework tells you where the 2 pi comes from. Then f of t, so if we make the same substitution, that s is equal to I omega, so omega is equal to s divided by I, d omega is equal to ds divided by I. So if s is equal to I omega, when omega is minus infinity, s is equal to minus I infinity to I infinity ds over 2 pi I e to the s times t f tilde of s. So this is if you're doing things with Fourier components, and this is if you're doing things with Laplace. So it's the same transform. So here I didn't write the lower end of the integral. Often, formally, what we're doing is we're just saying everything is off before time 0. And if f of t is 0 before time 0, we can put a 0 there. So that's why this integral with Laplace transforms often starts at 0, is that we are considering a system that before time 0 is equal to 0. For Fourier transforms, usually what we have to assume is that f of t goes to 0 at negative infinity and positive infinity. And what we did with the step function is sort of do the same thing, that says that this really is only well defined when the function f of t goes to 0 as t goes to infinity. So there are the transforms. We're good? We're good. All right. Okay. So so it's always good to check your answers. And with a signal that at long time goes to a constant value, and a system that is dissipative, that means that usually means the system should reach a steady state. So if the input's time derivative is 0, the output should also have 0 time derivative. So that's not always true. If we had a perfect spring, for example, and hit the spring with a delta function, then the spring will continue to oscillate forever as long as there's no damping. But most systems that we deal with will be damped, which means that, that at long time, if beta dot of t is equal to 0, then x dot of t is equal to 0. So we're not going to prove this. We're just going to assume that it's true for a dissipative system. And we're not really going to define what that even means. But what? Excuse me?
Keep that where everything goes to nothing in the world.
So we're not gonna this is not cosmology or philosophy, so we're not gonna we're not gonna discuss that in class. That's an after class discussion. All right. So what that means is that here for a step function we have x dot of t is equal to beta of t minus alpha x of t, and say beta of t goes to beta 0 as t goes to infinity. So what that means is a quick way to get what the long time value should be is just to set this to 0 as t goes to infinity. So then we get 0 is equal to beta 0 minus alpha x, or x is equal to beta 0 over alpha as t goes to infinity. So it's a steady state. It's the steady state value. And then we compare that solution with this solution, and we see that as time goes to infinity, we lose this transient term, and we get the beta 0 over alpha. So this is something that's good to do to check that your answer makes sense. That, we check to see that, yeah, we get the behavior we expect at long time. Yeah, so this should be, x. So here, but as t goes to infinity. So x of t. So one issue I have with this, I haven't found good notation yet, is shorthand for the value of x as t goes to infinity. So in some books, it calls it x steady state. That seems to me like it's wasting a character. We should only really need one character in the subscript, not two. Sometimes it's called x sub infinity, which makes me think like that's a super big value of x. So I look at that and that just doesn't look right. We can have x, t right hour infinity, which is clear but takes up a lot of characters, or the limit t goes to infinity x of t, which is not an abbreviation at all. So I've been searching for a good abbreviation for x of t as t goes to infinity, but I don't have one. All right, so now there's one final input that we will consider, and so the final input, and there are two reasons to consider it. One of the most important, so here so beta of t is equal to beta 0 cosine of omega t, and we can also write this as beta 0 times the real part of e to the I omega t. So if you remember, e to the I omega t is cosine omega t plus I sine of omega t, and it makes calculations easy sometimes if you just write the cosine as the real part of e to the I omega t. So there are a couple practical reasons why this is a very useful input. If you're doing any sort of signal averaging, you can really get much better statistics with an oscillating input than either with a step function where you never get the step exactly right, or with an impulse where you have to worry about the width of the impulse. So this function really does a great job. And the other thing is that, mathematically, the operator that we're using, the time derivative operator, sort of just naturally separates different frequencies. And it's, since frequency domain functions are the eigenvalues of the operator, it lets us do things in a very natural way for any system that the time derivative is important. And so practically, the people who are doing these experiments that we'll look at are using sine. Actually, I'm not sure whether they're using sine wave or square wave. Sometimes it's sine wave, sometimes it's square wave. Sometimes it seems more natural for a person to do a square wave input as opposed to a sine wave input. I don't know, like if you're doing PCR thermocycling and you program in the temperatures of the two baths, it's usually a square wave switching back and forth, some minutes at one temperature, some minutes at another temperature, as opposed to a sine wave. So as a personal tangent, I'm older than my sister, and my sister is so old that, so she has a PhD in molecular biology, and she was doing her PhD when PCR was just invented. And instead of programming the thermocycler, she actually had two baths at different temperatures. And she was the thermocycler, like picking up her test tube from one bath and then walking it across to like the other bath and then doing that for, I don't know, like an hour or two. So it's nice we have thermocyclers now. Like I was shocked when I heard that. So here we go. All right. So beta of s is equal to beta 0 times the real part of 0 to infinity dt e to the minus st e to the I omega t. And we moved the real from here to out here because we typically think about s as pure real, although in the end it doesn't really matter. And so this is 1 over s minus I omega. And then for the real part, we multiply by s plus I omega divided by s plus I omega. So we get beta 0 s over s squared plus omega squared. So you'll notice we could have been plus or minus I omega t in the exponent. For the cosine, it doesn't matter. For the sine, we would have the imaginary part, and then we'd have to be more careful about the sign of the e to the I omega t. All right. So now, so I'll put it down here. So we get beta 0 s over s squared plus omega squared. And I'll erase this so I have more room. All right, so now we have x of t is equal to, so we have x of s, x tilde of s, is equal to 1 over s plus alpha x at time 0 is in height, plus 1 over s plus alpha beta tilde of s. So this part, we already know is just the decay of the initial system. So e to the minus st x at time 0, e to the minus alpha t. And so this will give us part of the time domain solution. So we're just going to ignore that to save space. So if x was not 0 at time 0, we have the decaying transient from the initial system. So then x at time t is ds over 2 pi I minus I infinity to I infinity. Then we get the beta 0 e to the st t, and then we get s plus alpha, s minus I omega, s plus I omega. And thinking about where the poles are, so here's our s-axis, so we're integrating up the axis. We have a pole at minus alpha, and we have a pole at minus I omega and at plus I omega. And now we have the same problem we had with the step function, that our poles are exactly on the imaginary axis. So the three standard choices are: we include all of the value of the poles, they move a little bit this way. We include none of the value, they move this way. Or we take the difference and take half the value of the poles. So the reason that the poles are exactly on our contour of integration is the same reason that we had with the step function, that our input never turns off. So if we took an input that instead of just was cosine omega t, we made it decay, we put an e to the minus epsilon t, then what we'd be doing is we're moving the poles just a little bit this way inside the contour. And so that's what we're going to do. So we're going to take the full value of the poles even though they're on the imaginary axis. So that will be what we typically do, because that's really the physical system that we're working with. So now we just add up the contribution from each pole. The 2 pi I cancels the 2 pi I that we'll get from going around each pole. So we get a beta 0. And then, actually I'll do the first. So the first term is a minus alpha. So we get e to the minus alpha t divided by minus alpha minus I omega, and then minus alpha plus I omega. So in the denominator, that's an alpha squared plus omega squared. So the first term we get is exponential decay. The reason we get this term, like if you sort of want to think about it a little bit, is that our system input looks like this. So our input looks like this. So this is beta of t. So this height is beta 0, is beta 0, so cosine omega t. So this time, omega t is equal to 2 pi. So this would be 2 pi over omega, and then 4 pi over omega. So this is what our input looks like for time after 0. For time before 0, our input is 0. So what this sort of means is, like, we get a transient from this part of the input being 0. If we had set up our system so from time negative infinity to infinity the input was beta 0 e to the beta 0 cosine omega t, then we wouldn't have this transient. So this is just like the system catching up to it wasn't seeing a cosine forever. So we're not going to worry about that term, because if you were in the lab doing this experiment, like really what you would be doing is, like, you'd set up your system and then you'd start applying your cosine input, and it'd take a minute or two for everything to stabilize, and then you see sort of a nice output. Or like imagine you're pushing a sibling on a swing and you're starting from nothing. So but you're going to give the same strength push. It'll take a while before your sibling is swinging happily and not complaining that you're not pushing hard enough. So, but then after a while, things will sort of even out and you'll be in a steady state. So this is just saying that you have to turn on the equipment sometime, and then if we wait enough time, this transient will go away and we'll ignore it, and then we'll just have the oscillating terms. So pure imaginary frequencies, or plus variables, gives us an oscillating term. So those will be a plus beta 0. And we'll do this pole first. So here we have an e to the I omega t divided by I omega plus alpha. And this is the one that gave us the pole, so that's what gives us the 2 pi I. And we got a 2 I omega. Oh, and I had the s up here. So beta of the input had the s in the numerator also. So remember that. So then in the numerator we get that I omega from that S. And then we do the other pole, the pole at minus I omega, and we get e to the minus I omega t, a minus I omega. In the denominator, we get a minus I omega plus alpha. And then we get a minus 2 I omega. So this I omega cancels that I omega. This minus I omega cancels that minus I omega. And one thing that's good to see is that these two terms are complex conjugates. So we had an input that's pure real, affecting a system that's pure real. So the output should be pure real. If you do something and you get an imaginary part of the response, in this class it will mean that you almost certainly made an error. Yeah?
The 2I omega and negative 2I omega, is that just you have the I omega and can you just go over that?
Excuse me?
Can you go over how that?
Yeah, all right, so let's say we're working with this pole, all right? So what that means is that we look at the rest of the function and we say, is the rest of the function well behaved when s equals I omega? And the answer is, yeah, the rest of the function is well behaved, okay? If it weren't well behaved, like if the rest of the function went to 0, then we'd have to pick out the right residue. And we'll do that in the cascade example. All right, but here, the rest of the function is well behaved and this exponent is 1, so we're good. So we could think about that as a function. So then essentially what we're doing is we're thinking about then writing it like this. So we have a ds over 2 pi I, and we're thinking about doing a little contour around s is equal to I omega. All right, and now we have a function g of s divided by s plus I omega. All right, and around I omega, g of s is well behaved, so we could just write it as g of I omega. So then when we do that little integral, we get the 1 over 2 pi I, then g of I omega, and then times the 2 pi I for going around that little contour. Like you saw that if you integrate around a contour, if you integrate a contour around a simple pole, you get 2 pi I. All right, so those cancel, and we just get g of I omega. So in this case, g is equal to e to the st times s over s plus alpha times s plus I omega. So it's everything except that simple pole, because that is over here. And then if we just substitute in I omega, we get e to the I omega t times I omega divided by I omega plus alpha, and then I omega plus I omega. All right? So if you substitute in, and the pole gives you a 0 or an infinity, that means you did something wrong. And what you did wrong is that it wasn't a simple pole, and you have to go back and think about what you're doing. Yes?
Why are we allowed to do it that way? What's the general method of explaining out into fractions, or could you refresh?
So why are we allowed to do it that way?
Yeah, analyze that.
Okay, so in the lecture that we had 1 lecture ago or 2 lectures ago, we saw that it is very odd that a contour integral, we saw that most if a contour integral of integer powers gives 0, except for if there's a pole, like if we can express something as a power series. And we also saw that we could do the Laplace transform as a big contour in the left half plane. So then what we're doing is we're saying, we have these poles, all right? So just these 2 imaginary ones. And we're doing this big circle, all right? So now, imagine instead of doing that big circle, we did a little cutout here and a little cutout here, all right? So now, with these little cutouts, the integral around the contour is 0 because our function is well behaved in that region, all right? So the integral we want is equal to, 0. So I'm sorry. So the integral minus these two little loops, minus loop 1 minus loop 2, is equal to 0. Where this is loop 1 and this is loop 2. So if we take the integral, is it minus or plus now?
Those little poles that can go into infinity, right?
So that's our integral plus loop 1. So our integral, and then if we add on these little loops, integral plus loop 1 plus loop 2 is equal to 0. All right? Where these loops are what take us, or get the poles outside of the integral. So that means that our integral has to be equal to minus loop 1 minus loop 2. Okay? Now, so this loop actually is going in the clockwise direction. So minus the loop goes in the counterclockwise direction. So our integral is equal to the loop around one pole plus the loop around the other pole. And then we're just doing them separately and adding them. So there's another question.
And just how the poles are defined again? To go over that? Are they infinity or something? Or?
So the pole is where, if we do a Taylor series expansion, we get 1 over something to the power 1.
1 over something.
Yeah, so we get like an exponent of -1 in a power series expansion. So here, if we did a power series expansion, we get a -1 for a power series expansion around s plus alpha, a -1 if we're doing it around s equals I omega, and a -1 if it's around minus I omega.
Okay. So the rest of the function is just defined in anything.
So the rest of the function, as long as it's well behaved, we're okay.
Well behaved.
So well behaved means it doesn't go to 0, it doesn't go to infinity, and it has integer powers. So like if you do a Taylor series expansion of e to the st, you get integer powers of s. So you're fine.
What if you had something?
If you had a square root. So if we had a square root, then that would be a hard problem.
Okay.
But typically we won't have square roots.
We had something to the power of x.
If we have something to a positive integer power, it's usually fine. You know, the issue is if you have something that's going to cancel one of the poles in the denominator, like sine x over x is actually sort of, that's a little tricky.
Yeah.
Because,
They're both the same.
yeah, so like you have to think a little harder for something like that.
The limit is 1.
For us, what we have to think hard about is like sometimes we'll get higher powers in the denominator than 1, and then you get a contribution because when you do a Taylor series expansion of the numerator, then like you take one of the terms in the power series, but we'll get to that. We won't do that now. All right. So now we'll close that. So this term I'm just going to ignore. Yeah?
So I have one more question here. About that term, is that what shifts our contour so that we include the 2 poles, the imaginary poles?
Is what term?
That first term.
This term?
Is that what's supposed to be shifting it? Or?
No. So this term is just the contribution that we get because before time 0 we weren't pushing on the system.
Okay.
So after a long time, like the system will come to like a periodic steady state. But like right when you're starting, you're not going to be in the periodic steady state yet because you haven't had enough cycles of input.
Okay.
So how many cycles of input do we need? Does it depend on the strength that we're pushing it or the frequency that we're pushing it at? None of that matters. The number of cycles we need is e to the minus alpha t has to be small. So 1 over alpha is the relaxation rate of the system. 1 over alpha is the relaxation time. We need a time that's long compared to the relaxation time of the system. And then if we wait that long, then it's sort of like we've caught up and we're in a periodic steady state, periodic equilibrium with the input. So.
Okay, so because you mentioned like we're
what
shifts?
So what shifts it is so this input, you look at this input doesn't go to 0 as time goes to infinity. Any input that doesn't go to 0 as time goes to infinity will give us a pole on the imaginary axis. I think. So again, I'm not proving that, but I think that's true. Any input that doesn't go to 0. I mean, it's oscillating. So if we wanted to get it to 0, then we would put in, then what we would do is we put in e to the minus epsilon t. Then we get something that goes to 0 as time goes to infinity. And then we know at the very end, we would take epsilon going to 0, and hopefully we get the right answer. All right? And if we're looking at a time that's smaller than 1 over epsilon, it's like as epsilon goes to 0, 1 over epsilon goes to infinity. If we're looking at a time that is smaller than 1 over epsilon, then epsilon shouldn't matter anyway. All right? So if we did that, then we'd have the real part of e to the I omega t e to the minus epsilon t. Just the same way we did it with the step function to get something that was well behaved. And then here we'd get e to the minus st and then e to the minus epsilon t. And then we would get, instead of 1 over s minus I omega, 1 over s minus I omega and 1 over s plus I omega, we would get 1 over s plus epsilon minus I omega and 1 over s plus epsilon plus I omega. S plus epsilon plus I omega. And our cosine transform would be beta 0 s plus epsilon divided by s plus epsilon squared plus omega squared. All right? So if we have a cosine that we've, say, regularized, so at some point it shuts off, all right? Then our Laplace transform is s plus epsilon divided by s plus epsilon squared plus omega squared, all right? And so with that, and then if you take epsilon equal to 0, this is, pretty well behaved. Well, if you take epsilon equals to 0, you get back what you usually use for your cosine transform, all right? But here, this is saying that we're shutting off the signal as time goes to infinity, so we don't have any problems. We shouldn't have any problems with things not being well defined. Okay? And then, if you look at the poles of this, the poles are that, so we would have s plus epsilon plus I omega times s plus epsilon minus I omega. So our poles are that s is equal to minus epsilon plus or minus I omega. All right?
Right, so you're saying, so the epsilon is then what shifts it?
Yeah, so that's what shifts it. Yes. So what shifts it is that as time goes to infinity, our boundary condition.
Same thing as the step function.
That's right.
Okay.
It's the last one out, turn off the lights sort of thing. Eventually the experiment has to turn off. We don't do an experiment forever. Yeah.
So the first, just really quick,
Unlike lectures.
the first term of your x of t, should there also be a negative alpha there because?
Yes, there should be. There should be. Thank you. Yeah, so that s gives us a minus alpha. Thank you. Yes.
How is that?
So here, so when I did this, I forgot to have the s from the input up here. So when I did the inverse transform, I didn't have this minus s, so I didn't get the minus alpha. But really, there's an s there, and this is the contour around the pole at minus alpha, so that should be a minus alpha. All right, so this gives us a beta 0 over 2. So we'll pull out that 2 and that 2. Divided by e to the I omega t. And then write this as alpha minus I omega plus e to the minus I omega t divided by alpha plus I omega. So, it looks a lot like cosine of omega t, except we've got these terms in the denominator. So the way you deal with expressions like this is, So this denominator, essentially it's written in Cartesian coordinates. If we write it in polar coordinates, it becomes much better. So the way to think about it is we have this complex number. So here's alpha, here's omega, and here is alpha plus I omega. All right. Yeah?
How did you go from I omega plus alpha to I omega minus alpha? I mean alpha minus I omega.
I made a mistake. So where was I over there? Alpha minus my omega. There we go. Thank you. All right. So, so this is in Cartesian coordinates, and we want, and it will be easier if we get it in terms of some magnitude r and some phase phi, to write it as r e to the I phi. So, because then we can combine this phase with the phase omega t and get a simpler expression. So if you remember polar Cartesian transforms, this r is equal to the square root of alpha squared plus omega squared. So that's the length of this vector. And in this angle phi, what we know is that the tangent of phi is equal to omega over alpha. So phi is equal to the inverse tangent of omega over alpha. So that is a convenient transformation to use. So then this is equal to beta 0 over 2 square root alpha squared plus omega squared. And then we get an e to the I omega t divided by e to the I inverse tangent of omega over alpha. And then a plus e to the I omega t divided by e to the minus I omega t e to the minus I inverse tangent of omega over alpha. So really that's the inverse tangent of minus omega over alpha, but because tangent is an odd function, the minus can go outside. So what we get in the end is, so we can write this as e to the I times omega t minus phi plus e to the I minus I times omega t minus phi. And then if we group the 2 with it, then it becomes a cosine. So what we get finally is that our output is that x of t, so the non-decaying part of x of t, is equal to beta 0 cosine of omega t minus phi, where this phase shift phi is equal to the inverse tangent of omega over alpha. So we have a cosine in, we get a cosine out with a phase shift and then linear dependence on the amplitude with a square root of alpha squared plus omega squared. There. Okay, good. All right. So, so one thing to notice, just to make sure that we didn't make any math mistakes, is that we've seen before that at steady state, often we get often we've been getting a prefactor of beta 0 over alpha. So here, this has the right scaling that, the square root of alpha squared plus omega squared, that sort of would give us a 1 over alpha, or it gives us 1 over alpha when omega equals 0. So we have, the prefactor has the right units. And it's good that we have a cosine in and a cosine out. When omega is really, really small, so when omega goes to 0, omega over alpha is 0, and the inverse tangent of 0, so what angle has a tangent of 0? The angle 0 has a tangent of 0. So when we're pushing really slowly, phi is equal to 0, and we get no phase shift. So when phi equals 0, there's no phase shift. If we push really slowly, the system has the same cosine out, it goes in. Now imagine that we're pushing really, really quickly. So omega is big compared to alpha, then we have the inverse tangent of infinity, and we get a pi over 2. And the cosine of omega t minus pi over 2 is the sine of omega t. So we get a phase shift of pi over 2 if we're pushing fast compared to the system. So that actually is how you optimize energy transfer. And that's why, like, if you're pushing someone on a swing, you don't push them exactly how they're moving. Like, you push like a little before they get to the top of the swing, and then that's what gets them out further, as opposed to if you're like just following them as they're going through the swing, and then they complain that you're not pushing them hard enough. So that is where we will end for today.